So thank you so much. So in this video, we're going to be focusing on two things. We are still looking at electricity, which is due part of mains electricity. But in this video, we're going to be looking at heat loss or energy loss. Energy that is lost through radiation and through emission. And then we're also going to be looking at circuits, doing some calculations with current, power, energy, and stuff like that. So energy loss. So that's the first thing we're going to be looking at. So I'm going to do a quick recap in terms of energy loss, and then I'm going to give you some questions to try. All right. If you're looking for videos, if you're looking for tutoring, this is the number you need to call, that one there or this one, or you can just send us an email. Or alternatively, you can click on this particular website here. You can go into it, 11plusgcs.com, and then you can enroll for a tutoring. And also in that website, you can find past papers and other materials like that. So this is where you're looking. Now, let's have a look at this diagram here. Suppose that this particular box contains hot water, nearly boiling water, so maybe 100 degrees, very, very hot. Now, this box is going to radiate energy. It's going to release energy by radiation. If this box has got different colors on different surfaces, like this side says is shiny silver, and this side is shiny black, and the other side they say is white, then different surfaces will radiate amount of energy at different rate. Okay, and we can think about that. There's also this particular diagram as well, which I've got from the BBC Bite Size. Here we have what we call the infrared detector. Infrared detector is any detector that will detect any heat, thermal energy. So this detector, you can keep turning it around this particular box to see where energy is coming out a lot. And there is something you're going to notice, that as long as the energy is coming from inside, the side that is black will register much more energy. The temperature on the side that is black is going to increase quite quickly or faster than the side that is white. And what that means is that black surfaces or black objects, they cool down quicker. They are good radiators of heat. They are good emitters. They emit a lot of heat quickly. Those are black surfaces. So if I bring this infrared radiation this other side where the black is, the infrared radiation is going to register a higher value than when I take it on the white side, as long as the heat that is being released is coming from inside. The same thing is going to happen here. So black surfaces are good emitters, or they're good radiators. They release energy much more quicker than white surfaces. So if you have a cup of coffee that is white and there's hot coffee in there, that white cup of coffee will stay hotter for a longer time than the black one, because black cool down quicker. They release energy quicker. They are good emitters. They are good radiators, black surfaces. So that's the first thing I want you to understand. Okay. Now, before we move on to the question that I want you to try now, just remember that if you're looking for tutoring, it could be one-to-one tutoring, it could be face-to-face tutoring, it could be online tutoring, group tutoring. Just give us a call on this number here. That number at the top there, if you're in the UK or if you're calling from outside the UK, we can do it online. Just call us using that number, or you can just send us an email there with that email address. Or alternatively, you can click the link underneath this video in YouTube, and that will send you straight to our website, which is 11plusgcse.com. Okay, so that one can show you how you can link up with us. All right, so now what I want to do now, I've explained to you that black surfaces release heat much more than white surfaces. So with that one, I would like you now to try question 3, and let's see what you get. So try question 3, please. Pause the video and try question 3. All right, so hope that you've tried question 3. Now, one thing we need to know is that when you turn your computer on, because of the movement of particles, atoms, and electrons inside it, friction always happens and they heat up. So anywhere where there's electricity or current is running, because of resistance in the system, they will always be heating up. So this black drive will heat up, the white will heat up as well, but they're going to be radiating this energy off. They're going to be emitting it off. Now, black surfaces are good emitters compared to the white surfaces. So what's going to happen now in the first scenario, if you put this black at the bottom, then what's going to happen now, if you hold both of them together, they're going to feel much more hotter. It's as if the black is releasing heat a lot, and some of it is getting trapped in the white one as well here. So both of them are heating up, but because the black is blocking the white is blocking the black, and black is releasing much more, the whole system is going to feel hotter than in this particular case here. In this case here, most of the heating is going to come from the black one, and that's going to be radiated into the atmosphere or in the space. It's going to be dissipated in the environment, as you can see. So photograph B is going to feel a bit cooler compared to A. Okay. So with B, the hard drives are going to work, but if you hold them together, they're going to be cooler. Why? Because B is at the top. B is the one that is heating up, is the one that is radiating energy the more. A, I mean the white one always like a store energy. It doesn't release that much. But but black one is going to release much more. So in this particular case now, it's going to radiate it to the environment. So this one is going to be cooler compared to that one, right? So that is the idea now. So I'm going to show you the answers now to this and see how the wording will have happened. Yeah. So that is just what it is as is explained here. So the black is going to emit the more. Now, both of them are going to transfer energy to each other by conduction, isn't it? But that's not that much. That's not really significant that much. But the most important thing is this: you know that when the black is at the top, it's going to release much more energy to the environment than when it is at the bottom like that. So that's the point to this one. Okay. Now we're going to go to the next question. With the next question, we're going to be looking at circuits, and here I'm going to do a bit more. So here I've got two circuits that I've got from BBC Bad Sites. In the first circuit, this is a series circuit if you want. With the series circuit, there's only one loop. So this is series circuit and this is series circuit. So these two bulbs are in series. Why? Because when the current leaves here, okay, and goes like this, it passes, only got one pathway to pass through. So this is series, only one pathway, leaves through here and returns back through one pathway only. The same is this one here, okay, series. However, these ones are parallel. Parallel means that there's more than one path that the current can go. For example, if the current is coming through here and this is closed, it will go like this and can either go through this loop, can either go through that loop, or it can go through the down loop, this one. You see this? So the current has got two paths that you can follow. This is parallel to that. The same as this one. When the current goes here, right, the current can go like this. Look, the current can go like that. All right, and just come back. Can you see that? Or the current can even go down like this and then come back. So these are parallel circuits. Now, what is the advantage of series circuit? The advantage of series circuit is that there's only one circuit, and it's basic and it's simple. And you only need one switch to control them too. So one switch in a house will control the lights. That is basic, so it's cheaper. But in parallel circuit, each bulb or each pathway or each loop can have its own switch. So this has got one switch that will control this path, the same as this. So these particular bulbs you see here, they got only one switch that's going to control them. All right, like that. But this one, I can have one switch here, which will control this, and that, of course, in the way that they've set it up. But I could also have had a switch in this other one to control this one only. So with parallel circuit, you can have different switches controlling different components in that one. You see this? And then another thing good about parallel is this, that if one of them doesn't work, like say, for example, this bulb is not working, the current can just go down and this will just still work. But in this setup series, if one of them is not working properly, then both of them will not work because the current cannot go through a broken one. So this one won't work as well. So that's the problem with series. If one bulb is not working in your house, all of those bulbs will not light up. You have to replace the one that's not working first before the others can light on. But with the parallel, which is in most houses, that if one of the bulbs is not working, the others will just work. Parallel circuit. All right. Now, the other thing that I want to explain now is also in terms of something called power. I want to explain something called power. So this appliance at the bottom will have what we call power. Now, is given by volts times by current in electricity. So V times by I. So at the bottom, there'll be something written like, for example, 200 watts. Now, 200 watts means this, that every second, if this thing is working efficiently, it's taking 200 joules of energy from the socket to the water. That's what it means. All right. So 200 watts means that the amount of energy being transferred every second. That's what this is going to be. And we can work it out if you know the potential difference, the voltage. Say, for example, the voltage is 20 V and the current is 10 amps. Current is measured in amps. Now, when we times 20 by 10, we're going to get 200 watts. All right. So that's the first thing I want you to know. So power is given by V times by I. Very, very important. Okay. Now, the other thing now I want to work out also is something called, if I wanted to work out current, how will I have worked out current? For example, let's say that the power of this plants here, let's say is 500 watts, right? And I know that the current that's going, the potential difference across it, let's say is 250 volts. Let's pretend. And I work out the current that is going to go through it. If this is the amount of energy that is drawing per second, can I work out the current? Yes, I can. Power is given by V times by I. Power. If I want to make I the subject, I'm going to do P divided by V. P is the power, which is 500, and V is the potential difference, which is 250. If you divide that together, you get 2 amps. That means that the current that's flowing it through there is going to be 2 amps to deliver that amount of energy per second. Okay, so that is what there is. Right, so now what I want to do now, I want you to try this question that's going to follow. So I would like you to try the question that's going to follow. But before that, I will talk you through this one. I want to talk you through this before you try a couple of questions. Okay, now, in the house, actually, let me do this. Let's do the question first, and I'm going to run through this because otherwise it's going to take too long. Yes, I want you to try question 4. Just go to question 4 first. So pause the video and try this one. Okay, so I hope that you pause the video and you try question 4. Now I want to run through it. We said earlier that power is given by the current times by the voltage, VI or IV, same thing. So this is the power and this is the voltage. We can work out the current. So current is given by the power divided by the voltage, and the power is 200 watts or 2000 watts, and the voltage is 230 V. Just divide them, and that's going to be the current in amps for this part. Okay, now I think that when you divide this, I don't know how much you're gonna get this. I don't know unless I put that in, but it seems to me like something close to 20. Something close to 20. So he says, which of these fuses should be used with the heater? Now listen, we're gonna look at fuses in some other videos later. But a fuse is something that when the current increases too much, it will cut it to stop the current from flowing. So here, by looking at this, I think this answer, the way I'm looking at it, is approximately 17 amp. That's no, not 17. This is not even up to 10. Yeah, this is not even up to 10, I'm thinking. So this is not even up to 10. This is around, I would say around 7 or 8. Yeah, so let me just pretend it's approximately 9. Let me pretend approximately 9 amps. That's the current. Okay. Now, if the current that needs to flow here is 9 amp, then the fuse I'm going to use need to allow it. The 1 amp will not allow it because it's less than the 9. That will not allow it, that will not allow it. The only one that's going to allow it is going to be the 13 amp. So the fuse should be slightly more than the current that is required. So if the fuse is rated as 13 amp, it means it can allow current up to around 13 amp. So this 9 amp that approximated will need 13 amp, that will just allow it. If the current was more than 13 amp, then the fuse will just blow up. It will melt. All right. So the answer is about D. Question B, the two heating elements can be connected in series and in parallel. And I've explained this. We've said that in series is good because there's only one switch. It's cheaper. In parallel, you can use 2 switches. You can use 2 switches in parallel. And one will control one device, the other will control the device. And if one device is not working and they're in parallel, the other will still work. But in series, if one device is not working, the other will not work as well. That's the problem with that. Okay. Now, question C, I will just finish this video with this, but we're going to look at this later properly. Some electrical appliances are fitted with an earth wire. An earth wire is the one that is connected on the casing of the material of the appliance, and it takes the electricity straight to the earth. If there's a shock, if there is current that's flowing through the casing is a metal casing, like the outside of it, that current is dangerous because when you touch that casing, you can be shocked. So what happens is that if that happens, then the casing is attached to the earth wire, and that will conduct the electricity straight to the earth. And at the same time, the fuse is going to melt to stop the whole thing. But we're going to look at this at some other video later on. So in the meantime, I just wanted to mark this. In the meantime, just mark this. Okay, so I hope that has been marked. Now, we will leave it there now with this question. We're going to do this in another separate video.